Hello again. I thought some of you might be interested in how the solver for category morphisms actually work. I guess if you're not, then you get 10 minutes of your life to do something else instead now. But let's take a look. So we have the solver that helps us prove equations like this. And let's go and take a look at what the solver actually does. So the main idea is as follows, that we're going to define a syntactic notion of morphisms and then interpret it back into real morphisms. But the point is that these syntactic morphisms are something we can manipulate easily because they're just syntax. So then we can normalize these and we can show that the meaning of a morphism is the same as the meaning of its normalized form, which then means that it's really easy to show that two morphisms are equal if their normal forms are equal. And the process of translating these things to normal forms is what's going to do a lot of the simplification for us. So we're pushing a lot of the work into this soundness lemma for the normalization. But let's go back up and take a look. So what are the syntactic morphisms? Well, it's basically syntactic versions of all the categorical things that we know of. So we have identities, composition, and an F map applied to some syntactic morphism, where crucially the functor here is allowed to move to a different category, right? So it doesn't just have to be end of functors. And then we have two more things. So we have one way of embedding a real morphism into our syntactic morphisms, because otherwise this would be too restrictive, right? And secondly, we have this way of focusing on a particular part of a morphism. So we are putting our finger somewhere and we're saying, this is the part where I want to apply some rewrite. So that means that we can actually bracket our things differently and say that keep this part the same and be reflexive on all the other parts, for example. Okay, so then the interpretation of syntactic things into real things is quite simple. It's just doing what you expect. So it's sending the syntactic identity to the real identity, the syntactic composition to the real composition, etc., right? And then there's a little bit of a complication because we want to have arbitrary piles of functor maps. So not just one F map, such as here where we have one F map, but we want to normalize this into a pile of them. So here again we can just have 0 F maps, or we can have one more F map, right, where we already have a pile. And these can also be normalized. So if there are no F maps, then we just return the F, and if there's one F map, then we apply F map and continue normalizing. And this is the other important part of the puzzle, is that these syntactic morphisms are no better than the real morphisms, right? So we want to normalize these, and the way we do that is we are first of all going to remove all the identities and distribute F maps over compositions, etc. But we're also going to make sure that all the bracketing is done in a canonical way. So I think we're going to push all the brackets to the left. So canonical way to do that is to represent a composition not as made up from this composition operator, but just as a list of morphisms, right? And that's exactly what this star construction does. So this is star as in cleanly star, because it's the reflexive transitive closure of a relation. So in this case, it's a reflexive transitive closure of our syntactic, of our map pile relation, right? So the point here is that it's reflexive transitive, so you could either have none of these, then you have the empty thing, that's a reflexive bit, or you can have one of these followed by more of them, so that's the transitive thing, right? But the point is, so this is basically just a list of things that line up. That's the only thing that makes this not a list, is that these are for relations, not just for sets. So in effect, here we have a list of piles that line up. So this means that we exactly get this left nesting of all the brackets, right? Because a list is nothing but a left nested tree, if you want. And then all the actual work goes into this normalization function and below, right? Well, the normalization function itself is quite easy. So if we just have an embedded thing, then we can make a singleton. That's what return does. If we have the identity, then we make the empty list. And if we have a composition, then we normalize the pieces, and then we append the lists, right? And if we have an F map, then we do something slightly more complicated. But basically, we're just putting the F map in the right place, putting singletons, etc. And if we normalize something in focus, then we just continue normalizing underneath the focus. And here is where all the hard work is to prove the soundness of the normalization. So this is what we had to do manually if we didn't use the solver, right? So the work doesn't disappear, it just shifts into a different place, and that different place is here. Point being that this place is in the library, so we don't have to do it every time we use the solver, right? Okay. So that's the basic workhorse of the solver, and then to actually use it is quite simple, because you just say, okay, the point is that to show that d equals d prime, it's enough to show that the normalized versions are equal, which is much easier because this has to already normalized away all the different bracketings and identities and things like this. And the proof here is not so bad, right? It's just using the Soundness lemma. There's one other piece that's useful in the solver, just this idea of reducing a complex equation to a bunch of smaller equations. So the point of this is this reduced function. So it says that to prove that two identities are equal, it's enough to show that they are identities on the same type. And to show that two compositions are equal, it's enough to show that the first part are equal and the second part are equal. And this is the reason why we have this focus, because this means that we can put the focus in the right place. So if we put the focus in the first part of the composition, then that means that we get to prove f equals f prime, even if these are further compositions, right? And if it's not one of these, then we just say that the whole thing has to be equal. And then we have to show that if the reduced obligations are satisfied, then the things are really equal, right? So homomorphism is basically something we define for type inference reasons, so that we don't forget what we're proving. But it's basically equality of d and d prime. But this reduced function is the function we're using all the time, so that if we can prove the reduced equation, then we really know that d equals d prime, right? And then we have some convenience constructors. So we have something like reflexivity, which shows that d equals d. And it's called RD for R for reflexivity, D because it's applied to D, I think. Point is that it's short, so we can use it a lot without it taking up a lot of screen space. And we have RQ, which we use when we actually have something to prove. So we want to show that d equals d prime, and we know that the meaning of d equals the meaning of d prime. So this is where we inject all our real proofs that actually do something. And everywhere else we just can use RD. So that's what we saw here, right? So we put an RD for the boring bit, and then we used RQ to use the assumption that we had. Okay, and the rest of the solver is just packaging up the old equational reasoning in terms of what happens when you first interpret the pieces. So it means that you can write these things syntactically, and by using the reasoning you get that you really prove the meaning of the equality of the meanings rather than just the syntactic objects. But there's not much cleverness going on here. All the cleverness is here in the reduced function and here in the soundness lemma for the normalization. And it allows us to write proofs like this, where many of the trivial steps are really trivial, which is nice.